The next part in our sequence of talks about complex numbers concerns the complex exponential. This you might have heard of Euler's identity. And this is a justification of this celebrated identity that e to the I pi is equal to -1. There are many ways of approaching this. We will not really touch upon all of them. We will only define this object in a consistent way so that we can use it when we talk about Fourier series. If you look into the Wednesday lecture, you'll find a motivation there, and we'll see at the end of this talk, this video, that this is useful because it's difficult to work with sine nx, whereas e to the I on x will be a lot easier to work with. One is a geometric object, the other one is a trigonometric object. Okay, so how do we define this? Well, e to the z, we can split z into its real part and imaginary part. We can express this as cosine of x. We can express it in two parts. E to the x, cosine of y, plus I sine y. With this notation, it's worth noting two things. That the length of this vector, which is the x component squared, so e to the x cosine squared, plus e to the x sine squared, the y component, once you FOIL this, and cosine squared plus sine squared is equal to 1, so we're left with e to the x. So the norm of this element is e to the z, and if the length is r, then these components here are exactly the x and the y components. So the real part of this function, if this is expressed as u plus iv, the real part is cosine y times e to the x. So using that, well, what is argument of e to the z? Well, it is arctan of the y component over the x component. Well, that division cancels out the e to the x, so we get sine y cosine y. But this is exactly tangent of y, and tangent of y, arctangent of y gives you y. So y is the angle of this vector, angle that this complex number forms. Well, using this, we will mostly be working with x is equal to 0. And when x is equal to 0, we just have the imaginary part in the exponent. This factor becomes 1. And then we have e to the I theta is equal to cosine y plus I, cosine theta plus I sine theta. So if we go back to our geometric picture, this is the x component, sine theta is the y component. So these are exactly points on the unit circle, and theta is signifying the angle that you're making. So e to the I theta is a way of parameterizing, using complex numbers, the circle. As theta increases, you rotate counterclockwise, and theta decreases, you rotate the other direction. So this defines as a function f theta, which is a map from R to R. It is continuous. Why so? Because by the previous video, part 1 of this sequence, the components are continuous. And it is 2 pi periodic. So if you take theta plus 2 pi, you get e to the I theta plus 2 pi. And because cosine and sine y are 2 pi periodic, we get that this is equal to e to the I theta, which is f theta. So the intermediate step here is plugging it into the definition, cosine theta plus 2 pi plus I sine theta plus 2 pi. So this gives us a 2 pi periodic continuous function. And you could think now that sine n theta and cosine n theta are the familiar periodic functions that you know from real numbers. Well, the complex version, these can all be written as cosine n theta plus I sine n theta. So the exponential is an abbreviated form because it contains the best of both worlds. It contains both cosine and sine as parts of it. But contrary to sine and cosine, we have nice formulas for lots of the things that we will need to work with when we do Fourier series. One thing is we have nice product formulas. Now, if you add n plus m theta, well, on the one hand, this would be cosine n plus m theta plus I sine n plus m theta. And on the other hand, we can express it as the product of e to the I n theta, e to the I m theta. And if you expand this out, what do you get? Well, you'll get the real product of the real parts, so cosine n theta, cosine m theta, minus the imaginary parts, sine n theta, sine m theta. And then you will get the imaginary parts, which is the imaginary part of the first term, so sine n theta times the real part of the second, cosine m theta, and then plus sine of the real part of the first, so cosine n theta sine m theta. And what you'll notice is if you compare the components, here you have cosine n plus m theta, and here you have cosine n theta sine cosine. This is the sum formula for the real part, and this is the sum formula for that part. So this identity actually, and the proof would use the trigonometric identities, at least that's how we've defined things. It encodes within it both identities. However, it's easier to remember because it's a single identity versus two different identities to remember. Now, iterating this bound, if we multiply n times, so we raise to a power, then we get that e to the I theta to the power n is the same thing as e to the I n theta. This is useful for us because if you take sine theta to the power n, you don't have as nice formulas for it, but you have nice formulas for this. Another reason why this is nice is that if we call this equal a, then we notice that this is a to the n. So these terms here really look like a geometric series. We'll see soon how that is useful. Now, some things that are how it behaves with conjugation. Well, conjugation flips the sign of the imaginary part. So this would give us cosine n theta minus sine n theta I because of the conjugation. But this is the same thing as cosine minus n theta plus sine minus n theta times I. So this is the same thing as e to the minus I n theta. Now, if we want to, we can use this fact to recover then the real and imaginary parts. Well, the imaginary part of a complex number can be recovered by taking the number minus its complex conjugate. The complex conjugate is e to the minus n theta and dividing by 2I. So this is the same thing as e to the I n theta minus e to the minus I n theta divided by 2I. And cosine can be represented as the number plus its conjugate. In that case, with minus. So what we're using here is that real part of z is z plus z bar over 2, and imaginary part of z is z minus z bar over 2 essentially, but with an I because we insist that imaginary parts are actually real numbers. These identities are all that we need, actually, these 4 identities. So I want to give one example. This is worked out in more detail in the notes. But if you want to evaluate the sum of the first n sine n thetas, there's really no easy way of doing this. If you are very good with your trig identities, then you can do it. But contrast that to summing e to the in theta. This can be done considerably easier. Namely, this is the same thing by one of our identities above as e to the I theta to the power n. If this is our a, we can use the sum of geometric series formula to say that this is 1 minus the n plus 1th term divided by 1 minus the ratio of consecutive terms. So this is written just the geometric series sum formula. And if you check the proof of that, you'll see that that automatically works for complex numbers. So the fact that we're working with geometric things becomes very useful if we're looking at sums. And our ultimate motivation is to talk about Fourier series. So it's very nice to know that underlying here is a geometric sum that we can sum. So to see this calculation and to see how you can use this fact to actually compute the sum of sines, see the notes. This is not, we won't need this, but it's a useful fact, and it shows you how this works.